Hi, everyone. My name is Michael Weiss-Malik. It's my pleasure to introduce our speaker today, who's the Executive Director of the Focus Fusion Society. He's here to talk about his ideas on nuclear power, so please join me in welcoming Eric Lerner.
Thank you very much, and thanks for inviting me here. It's really an honor to be here, considering the distinguished scientists and engineers that have been in this Tech Talk series. So what I'm going to talk about today is focus fusion as the fastest route to cheap, clean energy. I'm going to start with a question, which is, why do we need a new source of clean energy? Why do we need a cheap source of energy, cheaper than any that we have today, since, of course, we do have things like solar and wind? If we look at the energy situation, the per capita energy consumption in the world today, we see there's an enormous gap between the industrialized countries, such as Western Europe, and most of the world. In Western Europe, the consumption is about 6.7 kilowatts per capita, the equivalent of roughly the equivalent of the energy output of 72 human beings. But if you go to India, that ratio is 5.8. In Nigeria, an energy exporting country, it's down to 3.4. To say nothing about our country, which managed to burn twice as much, or almost twice as much energy as Western Europe without achieving the same standard of living. So, considering that the average human being lives on $2 a day and suffers from really appalling conditions of poverty, the only way that poverty can be eliminated, the only way people could be brought up to the standard of living of the industrialized country, is by greatly increasing global per capita energy. To bring it up to West European standards, you have to about triple it. So what does that mean? Well, current global use is approximately 16 terawatts. So if we wanted, in the course of a generation, to provide everyone with a West European level of per capita energy production, we'd have to nearly quadruple energy production for a growth rate of about 6.8% per year. Now, with any existing energy source, that will be very difficult, because with fossil, nuclear, solar, or wind, it's very difficult to see that you can get less than about $1,000 per kilowatt in cost. At that price, it would take $2.2 trillion per year, more than quadruple current global energy investment. So basically, it would really be impossible with existing energy sources to achieve this goal within a generation, or even really within 2 generations. By contrast, if we have a cheap energy source, the energy source I'm going to be discussing today, we might be able to do that. Now, we don't have that energy source now. We need about a 6-year development period to bring it to a prototype, another 4 years to create a real industry around it, plus 10 years for implementation, the same goal. At the price that we think we can produce this energy source, $60 per kilowatt, that task could be achieved with only 3/4 of the current investment in energy globally. So that's basically the context. That's why we need an energy source that's clean and much cheaper than those we have today. Well, what is focus fusion? Focus fusion is the name we're using for nuclear fusion with a device called the dense plasma focus, using hydrogen boron fuel. And what's exciting about hydrogen boron is that it only produces charged particles. It's also referred to as PB11, P for the proton nucleus, and boron-11 for the most common isotope naturally occurring of boron. Well, if you've got boron, if you've got boron plus a proton, you heat it to very high temperatures, it fuses very briefly into an excited carbon nucleus, which breaks apart into 3 helium nuclei and no neutrons, and the release of about 8.9 million electron volts. Now, the reason that all charged particles is important is when you have moving charged particles, you already have electricity. you can convert the energy in those particles to electricity in a circuit basically through a form of high-tech transformer. You don't have to do what we've been doing since Edison, which is using heat to boil water, to produce steam, to run a turbine, to run a generator, all of which is very expensive. Instead, you can have direct conversion into electricity, which potentially can lead to an order of magnitude or more reduction in cost. Also, since you don't have neutrons from the main reaction, you don't have the production of radioactive waste. The fuel is abundant. Boron is adequate for billions of years of consumption, even at 10 times our current rate. And, of course, since this is nuclear, there are no greenhouse gases. So what's the catch to this ideal fuel? The catch is that it's very difficult to produce this fusion reaction for two reasons. One is, even as a fusion fuel, it requires exceedingly high temperatures, energies of more than 100 keV, which is the equivalent of 1 billion degrees, to ignite this fuel. And in addition, it has this problem of the X-ray emission. The X-ray emission tends to cool the plasma. X-rays occur when an electron collides with an ion, and the amount of X-rays you get are proportional to the square of the ionic charge. So since the boron-11 nucleus has 5 charges, it's 25 times more effective at producing X-rays than the normal fusion fuel, which is deuterium plus tritium, which are isotopes of hydrogen. So you've got very serious technical challenges to overcome. So what I'm going to describe in this presentation is basically, first of all, to just briefly name the 3 approaches that are being used to burn hydrogen boron fuel, then narrow down to the approach we're using, the plasma focus. Describe why we think that we can achieve net fusion energy, go briefly into the reactor costs and designs, how we're going to test this, and finally wind up with a brief comparison with the 2 other approaches. Just briefly, there are 3 approaches to burning this ideal but difficult fuel. First one is ours, dense plasma focus. Our company's name is Lawrenceville Plasma Physics. About $500,000 has been invested in this approach, initially by NASA's Jet Propulsion Lab and later by private investors. The second method is the field reversed configuration collider beam, quite a mouthful. Company is Tri-Alpha Energy. This is the only approach that has had substantial funding. $40 million from Paul Allen, a name that's probably familiar and popular around here, and Goldman Sachs. And then the third approach is inertial electrostatic confinement, which some of you might have heard Dr. Boussard talk about last year. The company is EMC Squared, about $6 million mainly from DARPA and the Navy. And there have been other efforts in the same approach in universities. Well, the reason why we think that the dense plasma focus is a very exciting device is even though it's extremely simple, as I'll describe shortly, it has the capacity for enormously concentrating power. This is a pulse device. The entire process takes about a microsecond. So you actually, the input to this pulse device is quite significant, 100 megawatts per cubic centimeter. But due to the way it concentrates energy, the output is enormously more concentrated. During the short pulse that it functions, it produces 11 terawatts, comparable to the rest of the energy production of the world. And this is in a volume that's only microns across. So you get billions of terawatts per cc. Now, the way that the plasma focus accomplishes this is very interesting, as I'll describe. It does it through a series of instabilities, which which makes it very different from every other fusion approach. Every other fusion approach, the idea is to capture the plasma and make it stable, make it behave. And plasmas just don't want it to behave. They naturally become unstable. The plasma focus approach is to sort of go with the flow and use the plasma instabilities to concentrate energy. Well, this is a plasma focus. This is one of the smallest plasma focuses in the world in Santiago. But any plasma focus consists of a central electrode, which is normally made out of copper, a hollow cylinder surrounded by an insulator, and it's surrounded by an outer electrode, the cathode, which generally consists of a circle of copper rods. Now, this device is enclosed in a vacuum chamber, which is filled with the fusion fuel in gaseous state, and it's attached to a capacitor bank. And when the switch is thrown, the capacitor bank releases, in approximately a microsecond, a strong current going from the cathode to the anode, which ionizes the gas, turning it into a plasma. So what you see is a current sheath formed, which flows from the cathode to the anode. It interacts with its own magnetic field to force the current sheath rapidly down the barrel of the anode. And this is where you get the first instability. First instability is the formation of these dense plasma filaments. This is because of a thing called the pinch effect. In any plasma, when you have currents going in the same direction, they create magnetic fields that attract each other and sort of twist around each other to produce these dense filaments, sort of little tornadoes. And they're produced in counter-rotating pairs. And this is a photograph of them looking down the anode, and you can see their pairs. So already you've concentrated the energy which was spread out into the sheath into these filaments. Now, when the sheath gets to the end of the anode, the attachment point moves to the inside of this hollow anode, and the filaments have to fountain together into this focus area. And at that point, there's another instability. The filaments which are counter-rotating, start to merge and annihilate each other. And you get inductive forces that very rapidly move energy from the outside of this array to this focus region, until you get to and this is a photograph of the focus region. It's really a black and white photograph, just added the color for looks. But again, you can see that now the energy is being focused into an area, a region only millimeters across. Well, all that's left of these filaments is a single dense filament. And then a third instability starts because the filament starts to twist itself up, a little like a telephone cord. That's called a kink instability. And it kinks itself up until it forms this plasmoid. The plasmoid is sort of a donut-shaped array made up of filaments, which starts to compress itself. And now the energy is in a region only microns or tens of microns across. And this is a photograph in the X-ray, is not very good, of the plasmoid, but you can see its general shape. This is sort of like if you took an X-ray of an iced donut, but the icing was made out of lead. So the plasma is really in the shape of the icing in the donut, not the donut. The final instability is that the plasmoid itself, when it gets dense enough, radiation from the very center of the plasmoid can start to escape. And that causes a sudden fall in the current, causing a sudden fall in the magnetic field. Whenever you get a sudden fall in the magnetic field, you have to generate a huge electrostatic potential. That potential accelerates a beam of electrons out one end and a beam of ions out the other end. And the electrons, as they leave, interact with the electrons in the plasmoid, heat it up, they heat up the ions, and you get fusion reactions. So even though the plasmoid is destroying itself by emitting these beams, in the short time it lives, which is generally nanoseconds to tens of nanoseconds, you have enough time, because of its high density, to produce significant fusion reactions. And here's the whole process: the rundown, the filamentation, and then the production of the plasmoid and the beams that come out of it. So again, what you've had was a whole series of instabilities that lead to the formation of this very dense plasmoid that contains all the magnetic energy you fed into the much larger device. Well, the plasma focus has been around for a while, in fact, over 40 years. So why hasn't it already given us fusion energy? There are a number of reasons. The biggest is the funding has been very limited. Funding going into this approach is about 1/1000th of the funding going into the main tokamak approach. That's for a number of reasons. One is this instability approach is very alien to most funding agencies. It's not only that most fusion reactors, but most machines in general are supposed to operate in a steady state, in equilibrium. And we're not. This machine never reaches equilibrium. It's always in an unstable state. We're using the instabilities. So that's sort of strange. In addition, this is an extremely cheap device to build. A large plasma focus takes about $100,000 to build, $300,000 including all the diagnostic equipment. Now, you'd think that would be an advantage for the funders, but it really isn't. Funders generally like a couple of large projects. They don't want to fund hundreds of small ones. It's sort of what I've called the anti-Darwinian tendency in government funding. In addition, in the generation of the pioneers of this approach, people who would be in their 80s or 90s if they were still alive, there was a considerable internal dispute about how the device functioned. Basically, was the action in the plasmoid, this tiny region, which most people think today, or was it in this much broader millimeter-sized focus area? So that also discouraged the funders. And finally, and this was very important, for many years there was no good quantitative theory of how the focus functioned. These instabilities are quite complicated to understand. And so the scaling laws that predicted the functioning of the plasma focus were all empirically based, which didn't give you a lot of confidence that they were right. Well, I entered the field in the early 1980s, and I had known two of the pioneers, Winston Bostick and Victoria Nardi, who were at Stevens Institutes in New Jersey. So I had been aware of the plasma focus, and I also was very much involved in astrophysics, as I still am. And at that time, astrophysicists were discovering that quasars emitted dense jets of energy, which are always one-sided. This is a picture of a jet from at various wavelengths. Now, it was thought at the time, and still believed, that this was emitted from a black hole. But that couldn't have been the whole story, because you have objects like this. So it's very much like a quasar, with the very dense, well-focused beam, but it's not. It's what's called a Herbig-Haro object. And this object here is an ordinary star in the process of formation, a protostar. So there's no black hole involved, and yet it produces the same energetic, focused, one-sided beam. So I asked myself, I was aware of the plasmoid emitting its asymmetric beams, and I said to myself, well, maybe this is an electromagnetic process in which energy is concentrated purely electromagnetically in a process analogous to the plasma focus and emitted in that way. Well, I knew that to test this theory, I had to develop a theoretically based quantitative model of the plasma focus to extrapolate it over a couple of dozen orders of magnitude up to the quasars and the other astrophysical devices. So working with Victoria Nardi, that's what I did from plasma instability theory, which is based on Maxwell's equations. And it turned out pretty well. The predictions corresponded pretty well with the astrophysical observations. So once I had this quantitative theory, the obvious question was to say, well, would the plasma focus burn this ideal fuel, hydrogen boron? Since everybody in the fusion community knew that this was sort of the holy grail. And it turned out the scaling laws were very encouraging. For example, the confining magnetic field in the plasmoid turns out to be proportional to the magnetic field you start with at the cathode times the atomic mass times the atomic charge. So that meant with higher atomic mass and charge, such as boron, you'd actually improve the compression. It also meant, since the starting magnetic field was involved, and that's the current divided by the radius, if you just shrunk the device, making the radius smaller, you get a larger magnetic field, higher density, and better heating. So the next logical step was to do an experiment to test this out. And it took quite a while because Department of Energy funds almost nothing but tokamaks. But eventually we got funded in 1994 by Jet Propulsion Lab, who was interested in this because this would be an excellent propulsion system for a spacecraft. It would get you to Mars in about 4 weeks. So with JPL funding, we did an experiment at University of Illinois together with George Miley's group with a small plasma focus, peak current of around 0.6 of a megaamp. And we took the device whose outer radiance was 5 centimeters, and we shrunk it. And we replaced it with a device whose cathode radius was 2.5 centimeters. And just as the scaling laws predicted, we got about a 5-fold increase in fusion yield, confirming the predictions. So this was very encouraging. But to get close to the conditions we needed for break-even, we needed a bigger machine. And unfortunately, JPL didn't have the money to fund our bigger machine, so it took us quite a number of years to scrounge at government surplus. But eventually, in 2001, we did a larger experiment at Texas A&M, again with JPL funding. Peak current of 1.4 megaamps, which might not sound a lot bigger, but this device, the output scales as the 5th power of the peak current. And the results we got were extremely encouraging. This is the experimental apparatus. This is the vacuum chamber that contains the plasma focus. And this is some of the cables from the very extensive bank of 40-year-old capacitors we were using. So the results are here displayed compared with what is required to burn hydrogen boron fuel. This is the temperature needed for ignition. And this is the ratio, how far we need to go from this experiment in 2001. So we got within striking range of the ion temperature. We were actually above the temperature we needed for the electrons. We also were above the nanosecond confinement times that we needed. But we still fell a little short, more than a little, in the density of the plasmoid and the critical product, density times confinement time. This density confinement time product is a measure of how much fusion fuel you're going to burn. And we needed, as well, a higher magnetic field. So we got the temperature in the range we needed. We showed that we had confinement stability, that the ions would make about 2,000 cycles before the plasmoid destroyed itself. That there was a very high degree of balance, which we call force-free condition, between the magnetic field and the outward forces. And that this was stable against the fusion energy release. the fusion energy was being recycled into the confining field. Otherwise, the plasmoid would have destroyed itself in only several picoseconds. And in fact, it lasted 55 nanoseconds, thousands of times longer. Now, this just gives you a sense of why we're confident about these results, because we took a lot of data from each shot. I don't have time to go into all of these figures, but each of these is a different set of data taken every 2 nanoseconds from the same shot. This, for example, is the X-ray pulse measured. This is the ion beam. This is the energy input. And again, I'm not going to go into this in detail. We can discuss it in the question period if people are interested. But we had many different ways of taking each measurement, the ion temperature, the electron temperature, the density, and we were able to cross-check these for consistency. So we're quite convinced that we did get these good results. But there were some limitations to this experiment as well. First of all, we had a very low efficiency of concentrating all the energy into the plasmoid. Only about 1/100% got into the plasmoid. So we had a low fusion yield. We couldn't optimize the device because we could not, for mechanical reasons, change the radius of the anode, the central electrode. And the peak current was still too low. Again, we needed a bigger machine. Now, unfortunately, at that point, when we went back to our funding agency, we found that they had been zeroed out. And the entire program that was funding us and many other approaches was ended by the new administration. And in fact, all fusion research throughout NASA was ended in 2001, which was very unfortunate because we knew we couldn't get funding from the Department of Energy. So we started to try and raise money from private investors. And in these 7 years, we have not raised enough money for the next experiment, but we have been able to make considerable theoretical progress. First of all, we think we know how to solve the efficiency problem. Other dense plasma focus experiments, and there have been dozens of teams working on this device throughout the world, have achieved very high efficiency, more than 50%, but not at this high temperature. So we knew empirically this could be done with long electrodes and high velocity to the rundown. Well, the theoretical key was a colleague of mine, Aaron Blake's suggestion. He asked the very simple question that if you start out with these counter-rotating vortices and you end up with a single plasmoid rotating on its axis, where does the angular momentum, the spin, come from? Because in all systems, angular momentum is conserved. So I thought about that and looked at the literature, and turns out that the angular momentum comes from the Earth's magnetic field. There's a component of the Earth's magnetic field that runs along the axis of the plasmoid. And when the incoming electrons interact with that axial field, they get a boost that causes them to move in a circle, that conveys angular momentum to them from the Earth's magnetic field. And that circular current amplifies the magnetic field, and you get an instability which gives you the angular momentum. And for the right amount of angular momentum, you need an electrode that's about 7 times longer than its radius. Aaron had another good idea, which is why rely on the Earth? We can inject the right amount of angular momentum by a simple weak magnetic coil that gives you that axial field. So that gives us another way of increasing the efficiency to give you the right amount of spin. Because if you put too much spin in, you won't be able to compress it, and the whole thing will fizzle. So we think we know the solution to that problem. Now, the other big problem was the X-ray cooling problem, which many people thought couldn't be solved, that you would always have a plasma with boron in it that would cool off faster than you could heat it up. Well, we made a discovery about this, except it was a discovery that was made in the library and not in the laboratory, which was the magnetic field effect, which had been first formulated back in 1974 by Professor McNally and was applied in the 80s to neutron stars. This gets into a little physics, but it's important, and I think it can be understood fairly easily. At gigagauss magnetic fields, billions of times the strength of our own Earth, there's a quantum mechanical effect that reduces the rate at which the ions heat the electrons, reducing the electron temperature, and thus reducing the X-ray emission, which goes as the square root of the temperature. And this is how it works. First of all, when a charged particle interacts with another charged particle, collides, it can only convey momentum perpendicular to its direction of motion. In a plasmoid, or anything that's highly magnetized, the direction of motion of the particles is along the magnetic field lines. So you have to convey motion to the electrons by bouncing them off the electric field lines and getting them to spiral around them. Well, if you have a sufficient, third point is that ions can only convey energy to electrons that are moving more slowly than they are. Most electrons are moving much more rapidly because they're much less massive. But there's always a minority of slowpoke electrons that the ions can convey energy to. Now, if you have a sufficiently strong magnetic field, the momentum perpendicular to the magnetic field lines is quantized. You have angular momentum of the electrons spinning around, and angular momentum is always quantized. In fact, Planck's constant, which everybody's heard of, is actually measured in units of angular momentum. So you have a situation like this, in which you have the electrons and ions moving along the magnetic field line. And if the ion does not have sufficient speed or momentum in order to knock the electron into the next one of these quantum levels, called Landau levels, no energy will be conveyed from the ion to the electron. But for the electrons, the typical electrons that are moving much faster than the ions, they will hardly be affected by this. They'll have plenty of momentum, and therefore their efficiency at heating the ions will not be affected. So that the ions will heat the electrons at much less rate than the electrons will heat the ion. That means that the ions can be at a much higher temperature than the electrons, reducing the X-ray emission. If you briefly look at the formula defining this, the critical energy of the ions, below which this effect becomes dominant, is proportional to the mass of the ion times the magnetic field. So if we want, at the ideal operating temperature of 600 keV, this effect to be dominant with boron ions, we need a field of 2.6 gigagauss, which is about a factor of 6 times what we achieved at the Texas A&M. In that situation, the electron temperature can be as much as 20 times below the ion temperature, and the X-rays can be reduced by a factor of 4. Now, we pretty much know that the magnetic field effect works the way we think it does, not only because this is well-established physics, but because other experiments have tested it. In machines like this. This machine is a Z-pinch machine called the Z machine at Sandia Labs, quite a bit bigger than our little plasma focus. And in various Z-pinches, even though they haven't achieved these gigagauss effect, magnetic fields, the magnetic effect is important either because they're using a plasma such as an iron plasma that has a much higher atomic mass, or because their temperatures are much lower, or both. So we can compare in this chart the observed electron temperature with the predictions. The blue dots represent the observed electron temperature. The scale is keV, thousands of electron volts. The green dots represent the temperature that's predicted if you ignore the magnetic field effect. And the red dots are the temperature predicted taking into account the magnetic field effect. And there's pretty decent agreement between the predictions and the observation. In fact, if you average them, there's only a 10% difference. So we know the magnetic field effect will do what we say it does. So we put this into a series of simulations, computer simulations of the plasmoid, and we find indeed that the critical ratio of fusion power to X-ray power gets above unity, which means that the fusion reactions will heat up the plasma faster than it can cool down. The bottom scale is in units of about 3 nanoseconds for each of these divisions. So as a result, the plasmoid heats up, the ions heat up very rapidly, and they reach a peak right in the optimal functioning range of 600 keV. But the electrons are 15 times cooler. They peak at 40 keV. As a result, you have very good burnup of the fusion fuel. This shows the amount of fusion fuel remaining, and after about 9 nanoseconds, you have 75% of the fuel has been burned. So from these simulations, we can get the parameters of what it's necessary for a operating fusion reactor. I forgot my prop here. This is about the size of the anode, the inner electrode that we would expect for a functioning reactor. Very small. But what's most significant is that we will get about 1.8 times as much energy out of each pulse as we put into it. So when we've optimized this for a reactor, we can determine how much energy goes into an input pulse, the fusion yield, the losses due to conversion, which I'll get to in a second, the net thermodynamic efficiency, and the pulse rate that we need to pulse it at. For those musically inclined, this is E above middle C. And the net power output. Now, the net power output is small compared with our present-day reactors, which tend to be about 1 gigawatt. That's actually an advantage. It means a small reactor can be placed very near the load, even if it's a residential neighborhood, which reduces both distribution costs and increases the ruggedness of the system against blackouts. This is how we intend to convert the energy into electricity. There's 2 sources of energy. There's the ion beam, which will be fed basically into a metal coil, and the rapidly changing fields produced by the ion beam, which is pulsed, only a few nanoseconds long, will induce currents in the coil, which will be fed to a capacitor bank. Now, if that's all we did, the energy would be actually, as the beam exits the coil, would be fed back into the beam from the capacitors. But we're going to have very rapid diamond switches that will switch when the current has passed into the capacitors and will prevent it from coming back. And this will create a big electrostatic field in the coil, which will slow down the ions and convey their energy into the coil. We and others have estimated that as much as 80%, or some people have said even 90% efficiency can be achieved. By the way, this is very closely related to the technology we now use to create microwaves. The X-ray pulse, which carries about 40% of the energy, will be fed into this device, which consists of thousands of extremely thin metal foils. In each metal foil, the X-rays will bounce some of the electrons out of the foil, convey their energy to them, and the electrons will be captured in very fine electric grids and will give up their energy to the grid. The reason you need thousands of very thin foils is that the foils have to be thin enough so the electrons can escape without losing any of their energy. But since the X-rays are much more penetrating than the electrons, only a tiny amount of the X-ray's energy will be captured in each foil. So you need thousands to achieve high efficiency. We have a patent pending on this, and again, we estimate the conversion efficiency around 80%. We sort of think of this as capturing a quasar in a bottle. Now, we talk about putting this in a neighborhood because this will be an extremely safe reactor. Even though the main reaction produces no neutrons, there are side reactions, but they can be easily controlled. One is this reaction, which produces radioactive carbon, which has a half-life of 20 minutes, which means once the machine is shut down, you can open it for maintenance 9 hours later with no protection. Radioactivity will be down to background. You have this other side reaction, which produces ordinary stable nitrogen and a very weak neutron. You can shield against these weak neutrons with about 1 meter of water, topped by 20 centimeters of boron-10, which happens to be the other naturally occurring boron isotope, and which is a very good neutron absorber. So again, at the surface of this device, you would have background radiation. You could stand right next to it while it was functioning, although that probably wouldn't be advisable because this is a high-voltage pulse power device. But you wouldn't have to worry about the radioactivity. The radioactivity induced in the beryllium electrodes, we'll be using beryllium, not copper, because beryllium is transparent to most X-rays, would be very tiny, 5 microcuries if you leave the electrode in for a year. By comparison, that's about the radioactive content in the bodies of a classroom of children. So you really would not have to worry about it. No radioactive waste has to be disposed. These are extremely safe. And since they're pulse devices, they can't run away. The amount of energy created in a pulse, 50 kilojoules, is basically what it takes to run one of these light bulbs for 10 minutes. The only reason you get significant yield is because you're pulsing it repetitively very rapidly, and that's completely under the control of your circuits. We've done cost estimates based on current commercial costs of the reactor itself and estimated the other systems. This would be the cost of the reactor at very low volume production, essentially handmade. This is our estimate for mass production, which we think is very conservative because generally mass production cuts costs by a greater factor. And this is how we get the final cost of $60 per kilowatt versus $1,000 for existing sources of energy. Total electric costs, including labor, about 0.2 cents per kilowatt hour compared with 1 cent, there shouldn't be a decimal point there, per kilowatt hour with the cheapest of today's energy. This is the equivalent to gasoline, to petroleum at $3 a barrel, or gasoline at 8 cents per gallon. So this is truly cheap energy. There also is not very much in the way of materials requirements. You've got very concentrated source of energy, so these machines are not very heavy. The only significant demand is going to be beryllium, and even if you were producing 5 terawatts of capacity per year, which would be a global rate of growth of more than 30%, you'd only have to double beryllium production. And the beryllium industry is a very tiny industry. By comparison, for example, let's take a clean energy source that we have today, solar thermal. The material requirements for, producing as much energy as we need in the world are very significant and would require an enormous expansion of some pretty big industries like aluminum or glass for the reflector. If you're using photovoltaics, you probably could cut these demands by a factor of 10, but they'd still be quite large. So what do we need to prove that this works? We need a 3-year experiment, $2 million, building a 3 megaamp dense plasma focus. Basically, 3 people to run it and 2 additional scientists to work on computer simulations. The goals that we think we can achieve over those 3 years: high energy efficiency transfer with high temperature, achieving the very high magnetic fields, burning hydrogen boron fuel, and demonstrating scientifically that we've achieved net energy gain. If we could achieve all this, it would take, we estimate, another 3 years for a development program to produce a prototype. That's the engineering part. I want to briefly discuss at the end a comparison with the other 2 devices, and then sum up. The one that Paul Allen likes is a field-reversed configuration with colliding beams. This also has sort of a plasmoid, but it's much bigger and much less dense. 30 centimeters and about 10 billion times less dense. Confined by external magnetic fields, and into this plasmoid you put an accelerated beam of boron ions and accelerated beam of protons. They're trapped within the plasmoid and collide, producing the fusion reactions. The other approach is inertial electrostatic confinement. How many here, by the way, heard Dr. Boussard? Oh, wow. We've got some fusion enthusiasts here. Basically, the idea of this is you have these magnetic coils are used not to trap the ions directly, but to trap electrons that are easier to confine. The electrons, slight surplus electrons, electrostatically attracts ions. They're accelerated, collide in the central area, and produce fusion. And you hope they collide with each other before they hit the coils. This is a comparison of the latest experimental results from these 3 approaches. And the critical thing to look at is these variables: the temperature in electron volts, the product of density times confinement time, so-called n tau, or sometimes n tau t, the product of all 3. And if you look at this compared with where we have to go, you see that the dense plasma focus is actually millions of times closer to reaching the goal than the other 2 approaches, and has produced millions of times more neutrons. This approach has been run with pure hydrogen, so doesn't produce neutrons as yet. The easiest way to look at this is graphically. This is log of n tau versus log of t. The black dot is where we need to go to get ignition so that the plasmoid will heat itself up to the ideal operating temperature. This is where we were at our last experiment, the red dot. This is where the IEC is, and this down here is where the field reverse configuration is. So it's very clear that the distance to be traveled by these other devices is much greater than for ours. Doesn't mean we'll get there first, but at the moment we do have a bit of a technical lead. For comparison, this is the results of the biggest tokamak in America, the TFTR in Princeton, actually a little bit worse than our results, even though they had 10,000 times more money. Well, the unfortunate problem is we haven't been able to get the $2 million to do the next experiment. What we find is that when we go to potential investors, they say to us, 6 years until you have something that you can sell as a product. That's too long. We want a return on investment in 18 months, 2 years, 2.5 years. Which to my mind is a very peculiar way of thinking, because what you have here is an energy source that potentially could revolutionize the way people live on this planet. It could lay the foundations for eliminating global poverty. It could eliminate the threat of global warming. It's safe, and its fuel is essentially inexhaustible. for that sort of reward, 6 years doesn't sound like a long time. And as a matter of fact, many technologies take longer to develop. If you look at the pharmaceutical companies, the average drug that we take today takes about 12 years to go from lab to market. So what we're really looking for is an investor or some set of investors who have a long-term or at least a medium-term perspective and are willing to invest in a high-reward technology, even if there's risk involved. Since I've read the official company philosophy here at Google, which is to invest in high-tech, high-risk, worthwhile technologies, and to have a long-term view, hopefully we're discussing this in the right spot. So to summarize, the world has a need for a cheap energy source, a clean energy source that's much cheaper than any existing. Focused fusion can provide that route to a safe, clean energy source. It's the closest to net power of any approach that uses this ideal hydrogen boron fuel. And the next step is only $2 million away for proof of principle. So that's the story. I thank you for your attention, and I'd be ready to answer questions. Yes?
I have a question. For $2 million, you can do it in 3. For 20, could you do it in 1?
Well, I've been asked this question a lot. And I guess the answer is I don't know, but probably not. The development program probably could be compressed with more money. Crash programs can be done, but they're very difficult and they're ultimately very wasteful. The idea of a crash program is instead of doing A, and then if it doesn't work, doing B, and if it doesn't work, doing C, you do A, B, C, D, E, F all at once, even though you don't know which one will work. That takes a lot of money. The Manhattan Project took 4 years to go from the knowledge that an unlimited chain reaction was possible to a product, which was the atomic bomb. That took, in our terms, in our dollars, $20 billion and the resources of the United States government at war. Obviously, these things take time. Could we reduce this 6-year development time to 4 years? Maybe, but we need a lot more money. And it would be hard to estimate how much more. To my mind, it doesn't make sense. I mean, certainly for the research phase, it would be very difficult to speed it up. If we had 2 devices, we probably would not be going twice as fast if the device that we had worked all the time. Since we're building it out of new material with new capacitors and so on, we probably will go about as fast as we could. So the answer is maybe we could speed it up, but there'd be more risk of failure. Up here?
Yeah, it seems to me that you've got sort of a pulse device, and that all of your experiments are focused on sort of single pulses, seeing what kind of results you're getting. But in order to turn it into a reactor, you're looking at a continuous chain. So is there any consideration to how the reactor whether the reactor would last over a course of years, sort of the effect of continued stress on the device? Because we'd be looking at, hundreds of thousands of pulses.
Absolutely. That would be one of the main engineering considerations. The 2 main engineering considerations would be the cooling system. If you don't want to erode your electrode, I mean, the electrode can be changed out. But for practical reasons, you want your electrode to last at least a month. You don't want to be opening up your reactor and shutting it down for 9 hours more frequently than about once a month. To prevent the erosion of the electrode has to be cooled. Basically, roughly speaking, a beryllium electrode should be kept below something like 700 degrees centigrade so that it won't have a significant vapor pressure. That's very challenging because you're taking a lot of waste energy out of a very small region. We think it can be done, but that's the engineering challenge. The other engineering challenge is the conversion system. You have to make sure that you keep track of every joule and keep the conversion system up to around 80% efficiency, or else you won't have enough energy to run the next pulse and to get the surplus energy out. Now, this will always be a pulse device, but it's going to be rapidly, repetitively pulsed, and you will need to get these electrodes through millions or hundreds of millions of pulses. So it's an engineering challenge, but engineers are clever people, and I think that if we get through the scientific challenge, it will be possible. Okay, I think your hand was next.
You mentioned both copper and beryllium. Have the experiments that you've done so far involved beryllium, or were they still based on copper?
No. We've only been using copper. It's much cheaper. Also, you can machine it yourself. Beryllium dust is poisonous, so you need safety precautions to machine it. The only reason we'd be using beryllium is because of this question of waste heat and conversion. You want the X-rays to pass through the electrodes and into that onion-shaped device. If the X-rays are absorbed by copper, they're going to be absorbed in the very outer layers, and that is going to cause the copper to erode. And also, you won't have the X-rays available for energy conversion. So the beryllium would probably be used only after we get through the experimental phase, or at the end of the experimental phase. Okay.
A couple of questions about the X-ray power extraction. You mentioned that the technology by which you're extracting power from the X-rays is patent pending, which suggests it's new. How well proven is that, and what percentage of your output energy is coming from the X-rays?
Well, the exact way we use it is new. The principles are the photoelectric effect, which of course has been used for many years for energy conversion. So we're not inventing any new physics. A significant fraction of the energy, something like 40%, has to come from the X-rays. So we do need to get the X-ray conversion in order to get the whole process to work. But again, there's no doubt the process will work. The question is, how efficient can we get it? Yes?
The hibernating fields, which you traded out for very strong for the cyclotron radiation, if we can define that because of density?
That's right. Well, you've sort of answered your own question. The plasmoid is sufficiently dense that the synchrotron radiation is trapped. The physics is this. If the plasma frequency, which is the frequency at which electrons vibrate within the plasma, is greater than half the synchrotron frequency, which is the rate at which the electrons cycle around the magnetic field lines, the synchrotron radiation is trapped. It can't get out. And the plasma frequency is proportional to the square root of the density. So if you have a dense enough plasmoid, then it can't get out. And basically, the plasmoid balances itself, so it's right at that trapped level. Only a very small amount of the synchrotron radiation can get out. And that's clear from many experiments. If the synchrotron radiation could escape, the plasmoids wouldn't last even a picosecond. Yes, back there?
Yeah, could you comment a little bit about the practicality of the engineering of a capacitor bank that can pulse 3 megaamps at 300 hertz? In other words, you need advances in capacitor technology to pulse the thing.
No. We're using, for our experiment, we're buying commercial high-energy capacitors. Now, these aren't things you can buy at Radio Shack, but General Atomics, which acquired a company named Maxwell, produces them as a regular product. And certainly, 300 hertz is not an excessive pulse rate. That's pretty slow considering the pulse itself is only a microsecond. Again, what you have to worry about is any waste energy from the electrical resistance of the capacitor. You have to have a cooling system to keep them cool. But no, that's commercial technology. Okay. You first?
So on your final plots, you had your device versus the IEC device.
Yeah.
So one of the nice advantages of the IEC device is all of the ions happen to be sitting in exactly the right cross section for the actual using of that. So my question is, when you look at not just the confinement time times the plasma, but confinement time times the energy times the percentage of ions that are actually at the cross section, who actually is ahead in that sense? Because your approach essentially relies on still essentially a high density approach rather than having the IEC approach, which is having all the ions in exactly the right cross section for fusion.
Well, first of all, even in the experiments we've already achieved, we've gotten close to the temperature needed for ignition. Once you get ignition, the plasma starts to heat itself up. And at that point, as you see from the simulation, when the conditions are right, the plasma will pretty much hold itself at the ideal temperature, at least briefly, for a few nanoseconds, because if it gets hotter, the reaction rate will slow down and it will cool itself off. So you've got basically a brief period of metastable equilibrium. So we're going to be pretty close to the optimal energy as well. The main thing is that the IEC has not shown that you can confine the ions for anywhere near the length of time so that they have a reasonable chance of fusing. They have to improve their confinement by something of the order of a factor of 10 billion. And that means they really haven't proved that the physics is there. I mean, you can have scaling laws, but you certainly haven't demonstrated them. Yes?
I was going to ask about the fuel. I mean, how you have to refresh the chamber for each pulse?
No. That certainly wouldn't work because you're burning only a tiny fraction of the gas in the chamber. What you would have, the gas we use is a compound called decaborane. What you would have is the chamber in contact with a source of fuel, and you'd be very slowly leaking the fuel in to compensate for what is exhausted. And what's being exhausted is being exhausted in the ion beam. You're going to have mainly the helium products and a little of the unburned fuel exhausted with each pulse. So the helium could be collected wherever the slowed up beam lands. So it would be a continuous process even though the energy release is pulsed.
Thank you, everyone, for coming. If you'd like to join us for lunch afterwards, please come up to the podium or for further Q&A. Thanks.
Thank you very much.